Carlos asked me to talk about storage in general in Kubernetes and OpenShift, but it was meant to be a storage 101, which is pretty basic. I don't know what's your experience with OpenShift or Kubernetes, but this comes from a very low level or basic level and goes to some of the concept that you will use in Kubernetes or OpenShift, right? But the main content here is on the Kubernetes level, not an OpenShift, but this is a generic Kubernetes. So you have a Kubernetes cluster, and you have the nodes within the cluster that will run the pods, right? Now, if you want to run application in a Kubernetes cluster, you will typically run it through the concept like a 12-factor app, in which application are meant to be stateless. Why we want that application is to be stateless is that so that the application can scale horizontally and become more flexible, so that you can have the capacity not bounded with the number of instances, so you can scale horizontally infinitely. But in a real application, data should still need to be stored, right? So that is where we start talking about storage in this application, right? One of the way that application can work with data is if they have an external database sources. So you can have a database as a service, and the pod will connect to the database sources or an external object storage or anything, right? So you can have a persistent layer outside of the cluster, and then everything inside the cluster is still stateless, which is allowing it to scale. But not everything needs a large infrastructure outside that you can have it. It might have some penalty in like latency or maybe scaling. So we start with an internal storages inside of the Kubernetes cluster, something that we call a persistent volume. Basically, it's a persistent volume is a disk storage carved out of a larger storage that you can use within the cluster. That's a persistent volume. You can create it by a path, a host path, or just create an ephemeral storage in the container file system, or anything, or an NFS storage or something. Right. Now, for example, you have a different persistent storage in the cluster with the different sizes, like you have a 1, 2, 5, and 10 gig, right? And then you have a deployment there that needs a 1.5 gig of a storage. Then what happens is the deployment will request a claim, and that will match. It will be matched by the system to the closest size and closest access mode and closest specification. So in this case, a 1.5 gig of storage will be stored in as a persistent volume claim within the 2 gig persistent volume. And then if any other things ask for the same 1.5 gig, it will occupy the next available size, which is the 5 gig one. And this is what we call a static or manual provisioning. So in this case, you have a set of physical volume that are already defined in the cluster, and then the deployment or the pod or any other workload that needs a persistent volume will try to claim that, and hence create a persistent volume claim. That's why the name persistent volume claim comes, is because the pod will claim the persistent volume to associate that with the actual storage. That's kind of the differentiation between PV and PVC, right? Now, as you can see, that this mechanism is cumbersome, that you have to create the PV or carve out the PVC first, the physical volume first, and then the PVC will claim that. And this is also not scale, because every time you need to ask for a claim, you have to ask for, you have to create a PV first, or either you have that or you can have to pre-create a lot of PV, and there are wasted storage. As you can see, the PV size is not exactly the same as the PVC. So then we come to something like the storage classes. So when you have a storage class, you will create something like a provisioner. So something that can provision storage. For example, you have a storage class 01. This is a mock storage class. So this can be anything like a GP2 or minutes NFS or anything. But now if a deployment needs a 1.5 gig of storage class SC01, what happened here is that the provisioner will create a PV with exactly the same size as is requested. And once it's allocated, then a PVC is associated with the deployment with exactly the same size. So there is no storage wasted, and you don't have to pre-create the PV. And the Cloud Pak and IBM Cloud Paks are using this technology. There are some mechanism or some storage classes that did not support this, but that means those storage classes that did not support the dynamic provisioning like this will not be supported for the Cloud Pak. So if another deployment needed another 1.5 gig of storage, the provisioner will create the PV, and then the pod will allocate the PVC and claim that and bound it to the pod. So that is where the dynamic provisioning concept starts. Now, you might have heard of the PVC types. So you can see there are 3 types of the PVC or PV in that sample. So every PV and PVC has to match the types. The read-write ones is when the volume can be mounted as read-write by a single node. Read-only many, that means the volume can be mounted as read-only by many nodes. And read-write many is that the volume can be mounted as read-write by many nodes. So one important keyword here is that the ones and many are not related to pod, but related to nodes. So for example, if most of the deployment needs a storage, they would not want to do a read-only. Just imagine that, right? So if you have a deployment, you need to store data. That's why you need a persistent volume. If it's only a read-only, why would you really need a physical volume? So in that case, this deployment here, the pod is in the different nodes. So if they want to write, both of them need to write or store data in the PVC. That means it has to be a read-write many. While this pod here is on a single node. So the PVC can be a read-write once, but both pod can write the PVC. So that is one differentiation. that the read-write many is and the read-write once is the differentiated by nodes, not by pod. So you can still have multiple pods as long as it has affinity to a single node. They can write, both can write to the PVC if it's on, even if it's a read-write once. That is also one thing that you need to take care when we install IBM Cloudpack or something, that some of the storages does not support the read-write many. So this is kind of the list of storage that's available in OpenShift for .7, for .8. I haven't looked at for .9 whether they change. The first part is the platform neutral. That means it's available on any provider, while the lowest part is the platform specific. So all of them will support read-write once. Only a couple of them will support read-write many. So NFS support read-write many, but it did not support dynamic provisioning. So there are several of these that does not support dynamic provisioning. Something like a host part will not support read-write many because it's only available on a single host. One generic things that support the read-write many is OCS, and I should have added Portworx there. And for other places, Azure has a Azure file which support read-write many, and VMware, GCE, and AWS is also only support read-write once. So this matrix kind of influence what can we do with the storage on a certain platform. So if you have heard about container storage interface, so what it is a storage that is provided by, there is a driver daemon set. So each node will have a driver that allows you to provision storage. What different is this from a standard storage? For an application developer, the answer is none. The difference is on how Kubernetes treat the CSI. The CSI is run as a plugin on the Kubernetes cluster, while the non-CSI storage is in the base Kubernetes code so that they don't need a driver daemon set. But the infrastructure will still be the same. You still create a request, and then the storage class will create the PV and the PVC as discussed in the earlier slide. But CSI is just a more generic way that people can write codes so that they will support the driver and will allow them to be used by Kubernetes. So it's make it the Kubernetes more extendable. That's why the new drivers are all CSI based, while the older one is not. Okay, now we get to a little bit different side of that. Storage. Now we have storage. You have data inside the cluster, but the data is in the cluster. So how would you perform a backup, or how do you save the status of the data? This is where the Velero comes in. Velero allows you to do a data protection, data migration, and disaster recovery. So what happened here is you have a Kubernetes API that talks with etcd, right? That is how Kubernetes works. And you can have a backup controller, which is a Velero, which will talk using the Velero CLI. So Velero backup you create a backup, and you save that into a kind of an object storage. So you upload the data out into an object storage. So the Velero has to be initialized to have a back-end backup storage, which is typically object storage like S3 or Minio or other thing. Or Nuba. I have worked with a Nuba as a backup storage for Velero. And it allows you to do a snapshot. So what happened is the disk is collected by Velero, and the image of the disk as is will be stored as a snapshot outside of the cluster. That's why you can use it for protection or migrating data or even disaster recovery if you can ship the object out to a disaster recovery site. Another method for doing backup is Spectrum Protect Plus. The Spectrum Protect Plus is an IBM product that is actually can drive Velero to talk with the PV and PVC and back up the resources, and do so with a policy base, so you can have a retention, automated schedule, resource role-based access control on which storage to back up and which storage are not. So that is kind of what the Spectrum provides you, is another layer of automation for Velero, because Velero in general is command based. So you have to create a set of a script, or it's just a set of command or cron job to run the backup. While with Spectrum, you have all the automation that can drive there.